But in any case, if we dive into the actual optimization and we want to improve the resolution, here we have a partial separation. It's about 50% baseline. The initial screening was done under extended range conditions, methyl tertiary butyl ether with 2% ethanol. If we wanted to increase the resolution, we would want to increase the retention. We need to decrease the solvent strength. So we could drop out the 2% ethanol and increase the amount of nonpolar component in the mobile phase, which would be hexane in this case, make it 50-50 hexane MTBE, and we have a nice baseline resolution, something that we could probably even consider adding back in maybe 1% ethanol or increasing the amount of MTBE to get these enantiomers to come off a little bit faster to help improve our analysis time. The opposite of that, like that OZ case that I showed before, if we have a great separation, but the analysis time is simply far too long, we could increase the solvent strength and get these things to come off a little bit faster. So our screening was done initially with 20% hexane, 80% DCM. If we drop out the hexane, just do 100% DCM, we can save ourselves in about 5 minutes or so on our analysis, but still plenty of room to be able to push these together even farther or even closer. So if we just add in 1% methanol, we get everything to come off now in less than 6 minutes, still have nice baseline resolution, and now we're saving ourselves an order of almost 20 minutes. So increasing the polar component is obviously going to push things off the column faster, and increasing the non-polar component, which is usually hexane, will get things to retain longer. So depending on what optimization you need to do. I mentioned temperature before as potentially being helpful or not helpful. We know that if we increase the temperature, we often have kind of a sharpening or a focusing of the peaks. So we will see a decrease in the column broadening. We will see the analytes coming off the column faster. So even though we're sharpening the peaks, we might actually lose a little bit of resolution because we aren't retaining the analytes as long. And the opposite of that is decreasing the temperature. Decreasing the temperature will retain the compounds longer, but in doing so, we will see potentially some significant column band broadening, and so our peaks will become more diffuse and we could lose resolution that way as well. But this is where that experimental design approach is important. You'll see kind of for your analytes what the effective temperature actually has to see if it's helpful or hurtful. In this case here, you see our separation initially at 50-50, 25 degrees C. Decreasing the temperature at 15 degrees C does result in some improvement in terms of the retention, but it does also broaden peak 2 quite significantly. And increasing the temperature to 35 degrees does sharpen the peak, peak 2. It actually doesn't have all that much effect on the resolution here, at least in terms of the elution of peak 1, which is helpful in this case. So this might be one where you'd consider running it at a slightly elevated temperature to help optimize your method. Increasing the column length does help improve resolution. However, it's not one-to-one proportional, meaning if you increase the column length by 2 times, you will not see an increase in the resolution of 2 times. That is because the resolution increases by the square root of n, where n is the number of theoretical plates. And so as you increase the column length by 2, you'll see an increase in the number of theoretical plates by 2, but the resolution only increases by the square root of 2. So it would only increase by 1.4. That's why when I said increasing the column length might help you in those separations where you are almost baseline, but it might not help you in those cases where you have a partial separation, say of 50%, or certainly not the cases of 10%. You'll need to do some other optimization before you look at going to a longer column. As an example of that, here are 2 chiral pack IB columns. Both are 5 micron. The top example is a 150 millimeter length. The bottom example is a 250 millimeter length. There's obviously going to be some differences between the columns because, as I said, they are 2 different columns, so there's some differences in terms of packing. But if you were to compare the separation factor and the selectivity of those columns, you see that for the most part, they're in the ballpark. Slight differences, again, arising potentially just from packing. But if you calculate the resolution, you'll see that there's an increase in the resolution going from 150 to 250 of approximately 1.3x. And so we're increasing the column length by 1.6. You increase the retention by 1.6. You can make the calculation for yourself here in the retention times, but the resolution, as expected, is only increasing by 1.3. In this case, obviously things were baseline resolved, so it's not as helpful. But in the case, like I said, of partial separations, it may or may not be all that you need to get a baseline resolution. Mobile phase additives, talked very briefly early on with the prolicane example, the fact that it was a basic molecule, so we included DEA in the screening. But what additives do we generally recommend? For an acidic analyte, we're going to look to add an acidic additive like TFA, acetic acid, or formic acid. For basic compounds, DEA is usually a great additive, but we can use something a little bit stronger if need be, like TEA or ethylene diamine if it's a particularly strongly basic molecule. We can also consider using TFA, in which case we would not actually be separating the free base. We would be separating the TFA salt, the ammonium salt of that molecule, which under analytical conditions is not a big deal, but if you were looking to scale up to a preparative scale, you would need to consider adding in some kind of a workup at the end of your separation to neutralize the compound. And then for amphoteric molecules, things like amino acids, we often find TFA works the best. And so again, you'd be purifying the ammonium salt. You would need to implement potentially some workup at the end if this was for a preparative separation. Typically 0.1% is sufficient to give you improvements in terms of peak shape, but you can go up to 0.5% if you need to. We just suggest that you not go above 0.5% in order to maximize the column life. We do our screening taking into consideration the chemical nature of the molecule, but if you were to do a screening without it, in this case, a basic molecule without an additive, oftentimes you will see something like this where you've got, you should see two peaks, but you see in this case just one very long tailing peak. But just adding in 0.1% DEA in this example sharpens things up very nicely, and you now see a nice baseline resolution. Even if you were using an additive, it might not be the best additive. So in this case, separation of warfarin on OD used 0.5% TFA in the separation, but peak 2 tails quite significantly. It doesn't really tail, it's just very broad. But switching it to acetic acid gives you a nice sharpened peak, a nice baseline resolution.